Let's talk about what a series is. So next, let's talk about what a series is. I'm going to focus primarily on summations because those are most of our best friend when we're analyzing algorithms, but I must stress that there's other types of series out there. So for example, products. So very often we encounter series. So for example, if you're interested in analysis of algorithms, very often when you are counting up the number of operations that your algorithm performs, say for example in worst case analysis, oftentimes what you count up ends up looking like a summation. Not always, but sometimes it happens. Say for example, if you have a loop or a nested loop, sometimes you'll have a double summation sometimes. So often we encounter series. So often a series can be finite or infinite, just like we talked about with a finite sequence and an infinite sequence, respectively. Given an infinite or finite sequence, terms of the sequence sorry, I'm getting really excited here. That sequence is looking a little melted. Sequence are added or multiplied together. So give you the kind of the frank end goal in this process, okay? You can imagine I have some number of operations in the sense of a computer science kind of mentality. I have some number of operations from my analysis of an algorithm. I derive what we call a growth or complexity function. So if you're curious more about these, I have like an extensive series called Big O Bootcamp on the channel where all I do is go through how you can prove claims involving Big O and these complexity functions. The question is, how exactly do we write these things out? You can imagine I have some general or explicit term or formula that I use to represent these counts, and I want to add them all together. So, or sometimes even multiply them. We're going to focus on adding for us because that's what you run into almost always. So given terms, so imagine I give you a sequence where its terms are A1, A2, all the way up to AN. Their sum, which is a finite series, at least in the sense I've written it here, can be given by the summation, so this is where we get to pull this bad boy out. Summation, which is the symbol we use for summation is sigma, well, capital sigma. So it's written like this. So I'm going to lay out the convention here for you, okay? So we got a lower limit to the summation, where you can imagine this for my computer science oriented fellows. You can imagine it's almost like a for loop, okay? So you imagine I have my term. Now, in the context of summations, very often what you're adding in the summation is sometimes called a summand. Or summand. So this would be your term for your sequence. This is the lower limit. And what we write at the top is the upper limit. And let me show you how this plays out, okay? There's a lot of ways you can tweak around with this notation. So what I want you to do is match this like a for loop. So you start off with I is assigned M, and what we're going to do is we're going to incrementally increase the value of I by 1. So you can imagine this as AM plus, then what I do is I write out the next term that's one higher. You can imagine each time I'm just going through and iterating through each value of I, starting at M, and I go all the way up to N and include that. So this would be AM plus 2, all the way up to and including AN. So if you're not sure what you're looking at here, this M, imagine it's just a 1, and you get this right here, except we're just adding them up, okay? So that's the way I like to think about it. I imagine it like a for loop. And you might ask, Dan, are there any like tweaks you can make to this notation? I've seen some places where what you do is you introduce another box over another spot right here. And say you want to make it increment by, say, 1, or sorry, instead of just being 1, like 2 or 5 or something like that, you could put a number over here, but it's not nearly as common. Very often people will just throw that some way into this the summoned or term. So hopefully that is clear, everybody. Is that clear, everybody? Is that clear? So this is what a summation looks like, and this is how you could write it out. So it's just a sum of all the terms in the sequence. So you could think of this as the starting index and the last index or final index. Now you might say, Dan, does it really matter that it's a sequence per se? Now technically speaking, like for when you're using it, doesn't make much of a difference. The point is that each thing you got inside that summation is a term in some sequence. That's the big point I'm getting at. So let me give you an example of what one of these might look like, just because I've done enough abstract stuff here with you. I thought I would start playing around with this a little bit more. So I'm going to show you one of these. So I must stress that by the end of our tutorial here today, I'm going to show you actually why this next thing I'm going to show you here is actually why holds. So I'll show you a couple different ways to convince yourself that it's actually true. So hopefully one of them, I'll give you a couple different ways you can go about it, okay? So I usually like to show students the first one to convince yourself of this. But the second one is a way that if you're learning about mathematical induction, I want to show you how you can do that, okay? So here's just another example. So suppose I give you 1 plus 2 plus 3 plus all the way up to some positive integer n. I must stress that you could have it starting at 0. It doesn't make any difference. It's just a 0 there. So let's exercise that flex that we got from earlier. And instead of looking at these pluses here, imagine it just as a sequence. And I want to write a general formula for some integer for each one of these terms. And if you think about it, so remember, it starts off at 1. So you imagine this as the initial value it takes on. So it starts off at 1. And the final value in this, imagine it's just going through one after the other, is n, right? So it means that what should go right here then? I must note that the variable I'm using here is I. What should go here is the summoned. What should go right there? What's the explicit or general formula for each term in this sequence that's being added up? And I must stress that if you're ever not sure, again, you can always massage or simplify what you have over here. If it isn't easy enough to really play around with at first, do some algebra, play a little bit around with it. But this one, it's pretty straightforward, right? At least I'd hope. It's a nice classic. It's a classic. You just put an I right here. So notice that if you start this off at I is 1, you get 1. You increment I by 1 again, you get 2. Increment I by 1 again. Well, you put that in here, right? 3, 4, 5, all the way up to when you get to the uppermost value, this upper limit, n. Put n in for I, it's right there. So we actually have a name for this series here. It's often called the arithmetic series. So there's some variants of this that are also called this, but they all have the same kind of flavor to them. So this also gets its name after what's called the arithmetic sequence, which has a very similar form to what I have right here. You can, for example, have a multiplicative term in front of this plus a constant on the opposing side after you add it. But my point is that it doesn't make much of a difference. So you might ask, Dan, what's this all going to be about? Well, my point at this stage is I'm just trying to show you what exactly a summation looks like. I will give you a closed form. This is actually just a simple formula for which it only takes some small number of operations to perform, usually a constant number of operations to perform, to evaluate the overall sum. Because notice that if I imagine this intuitively, like if I was going to implement this on a computer, you could imagine it's just like a for loop, right? I just have like a variable and I go, oh, x is assigned x plus I, right? So I would just run through each one of them and I could return you the value, right? So you can imagine it like that if you'd like. But I can tell you there's a nice, very simple formula for this, and I will go through that delicately. So this is an example of a finite series. And I must stress the way that people would read this. So what it would be read as is this the summation from I is equal to 1 to n of I. Okay, so seeing that this is a finite series, I'll give you an example of an infinite series. So here's another one. It's called the harmonic series. It comes up every once in a blue moon. Sort of like a werewolf that comes out at you at the middle of the night and you go, ah, help me. So you only run into it really when it's too late. Believe me, I've analyzed some very, very interesting algorithms sometimes where it just comes out of nowhere and you're just like, whoa, I have to deal with this sucker. Or at least a flavor of it. This is what we call the harmonic series. It has a finite version as well. But this is an example of an infinite series. Do you notice I put an infinity there? That means there's an infinite number of terms in this. Just like when we talked about infinite sequence, I'm adding up an infinite number of things, okay? Blow your mind. So anyways, that's what a series looks like. And next, I'm just trying to think of where I want to go with this. There's always so many things to fun chat about here. Okay. I'll give you a couple bits of notation, then we'll start really playing around with some properties that we have for these things. Seeing as I brought up products. So a series that is a product of each term. I must stress that we use this capital pi, not like pie, this kind of stuff that's really lovely to eat. I mean the Greek letter, capital, we're using a capital pi. So just like we have a really big summation as sigma, we use pi, a big capital pi, to represent products. It looks like this. So it uses the same type of notation again. Have a starting index, you have an end index, and say for example I give you this. What it means is I'm taking A1 and I multiply it by A2, then I multiply that by A3, and I multiply all the rest of these terms together all the way up to AN. So just as an example, so that you know that this thing is just really not that obscure, this is also, here, let me write factorial. So here's just an example. So here's factorial. So if you want to write factorial in this way, here's factorial. So n factorial, it's written with this exclamation mark. You can define it like this. So you have the starting index. The lower limit, k is b1, and the upper limit is going to be n. And in each term in there, it's just going to be k. So you want to see what that is? That is just n times n minus 1 times n minus 2 multiply all the way down to 2 times 1. Pretty nifty, right? You thought you had to describe this thing recursively or something like that. Nah, this is another tool you can use to describe that. Normally when I teach factorial, I show what I have over there on the furthest right, and then I'll write it out recursively so that we can see an example of using recursion. So, one thing I want to point out is another thing. I always have so many things to show you. Let's talk about some properties that these series have. So I'm just going to list them, and I'm going to give you quick justifications for each one. So if you're not convinced by what I'm saying, I encourage you to take the argument I'm going to give you and write it out on paper. Okay? So I'm going to give you kind of a sketch of each one of the ways you'd prove these. Okay? So I'm just going to orally say them. I'm just going to like fire these things off. So, why? Because most of these involve just counting. And not too terribly sophisticated counting. Because counting can, as much as we like to think counting is a very easy thing to do, man, when you get into the world of combinatorics, counting does not become easy. It's a whole other beast. Man, I love combinatorics. But this doesn't need too much crazy justification, okay? So let me just give you some properties. We'll use these in some of our examples. Some properties. I was about to say some property. I'm like, oh, that's some property. It's over there. So some properties. So if we're given two sequences, AM plus 1, and so on. So it might be infinite, it might be finite. I'm just going to presume for our discussion, when I write out these properties, that they're going to be finite. So it will be eventually a finite term, at least in the formulas I give you. So I have AM plus 1, and I have BM plus 1, and so on. And I'm going to presume that these are numbers, these numbers are real numbers. So we're talking about fairly general terms here. So our sequences of real numbers. And C, so there's going to be another, you can think of it just as it's just a constant as far as we're concerned. But you'll see that it doesn't have to be a constant. It's just that it's not dependent on the sums. So you'll see, is any real number. So it just could be any real number. Then the following hold. Then the following hold for any integer n, which is going to be greater than or equal to m. So that's my cap, is n. I'm just capping off the sequences, okay? So here's the first one. So if I give you a sum, lower limit is m, goes up to n, ak. And I want to have a second sum. Sorry, I get very excited here. Let's go grab some water. Hopefully that didn't sound too graphic. So I have the same number of terms between these two. Notice the indices, they match each other. That's an important detail here. But I'm going to add the results of adding all these terms of each sequence. What you can do is you can lump them together, all their terms together, by adding them like this. So that means that you can take each one of those terms, you can add them individually amongst each other like this. Now you might say, Dan, what do you mean by this? So the way this very often gets used is actually that it's distributive. So if you look at on the right side, If you end up with something where you're adding or subtracting in here, when you're subtracting, make sure you watch carefully the sign. But when you do this, you can actually distribute or split this into two sums like I have over there. And you might ask, Dan, why is this true? So let's think about it. Just write out what the sigmas, like what these summations mean. So what this is saying is that you have AM plus 1 plus all the way up to AN, right? This right here means I'm going to take BM plus 1 all the way up to BN, right? So that's what this means. This is all what that means. So all I'm going to do now is do that trick I told you earlier about associating the terms with their indices. So look. And you can do this for each one of the terms because you can match them up. Now look what I did. So all you do is you take those two, add them together, you get one term. Take those two, add them together. Take those two, add them together. And do you see how this works? It's really just pairing each term up like this, and they have a common index, so I'm allowed to do it like this. So I could just simply rearrange the way I write this, right? So I could just simply, if you're not convinced by my fun little lines, here, I could do this. So I just reorganized them by listing them out separately. And since I can introduce parentheses, I can do that like this. And then you ask the question, what's the general or explicit formula? It's right there. Pretty nifty, right? So that's the first property. So this is going to be one of your best friends. If you're ever playing around with summations, it's one of your best friends. And I must stress that it doesn't matter if there's a plus here or a minus. If you have a minus, it'll become a minus right here. Just be careful though. Remember, this is a whole sum. There's a whole ham hog here. One very common mistake that happens that students run into is they accidentally redistribute the negative sign if they're doing subtraction. So they would have minus here, they put minus where the plus is, that's okay. The problem is that they accidentally regroup the terms and they apply negative signs to things that aren't negatives. So that's one right there. So I'm just going to make myself a little bit more space. So that's the first one. This is one of your friends. Another friend is that whenever you have a variable that is not associated with the index inside of this sum, so in this case that would be k, you can actually pull it out in front of the sum. So you can factor it out. So I can have c times the sum from k is equal to m to n of ak. So c times this is no different than me writing this. The sum from k is equal to m to n of c times a sub k. These are no different than each other. The way you could tell really quickly is notice that c has no relationship with k. So very often in algorithm analysis, even though I use a c to make it sound like it's a constant, which many times it will be, it could be something like n. Like notice n right here. Like this could easily have been n and you could apply this property. Notice it has no dependency on k. And you might ask, Dan, why is this true? Well, let's think about it. There's a very similar property going on here like property number 1. So notice here, if I write out the left-hand side, that's c times am plus 1 plus am plus 2 plus all the way up to an, right? what does it look like when I decide I want to pull that c inside the parentheses? I want to multiply it against each one of the terms, right? Because like you can think of it just like if I factored out c, right? If I do this now, I'll get c times am plus c times am plus 1 plus c times am plus 2 all the way up to c times an. Notice that each one of these is a term in the right-hand side there. Pretty nifty, right? So that's why that's true. So without getting too much into just some algebraic rules for you. And these are true over reals, just to be very clear. The things that are integers are the indices on the sum, okay? But most of the time when we're playing with stuff in our analysis of algorithm, most of the time these are going to be integers where there might exist constants that aren't. But that's okay. Third property, this one involves products. It's quite similar to these first two, so I'm not going to go too much into the detail about it. It's just products instead of sums. So I'm going to have the product starting k is equal to m to n for ak. Imagine I have another sequence where I'm going to multiply this. I'm going to put a dot in here just to emphasize this. Times this whole product. The product from k is equal to m to n of bk. This is no different than rewriting this where I'm going to have the product of each one of these individual terms like this. And I'll give you a quick rundown of why exactly this is true. It's almost the exact same reasoning I used here when we talked about property number 1. Do you notice something that's nice about multiplication is that if you write out what this means, well, this is am times am plus 1 times am plus 2 times all the way up to an, right? This right here is bm times bm plus 1 times bm plus 2 times times bn. What do you do with this? You just regroup them like this. See, pretty nice, right? So those are some properties of series, okay? So many of these get used in algorithm analysis. And you might ask, Dan, what is a common or what is a closed form? So I use the word common just to be clear that these are ones that you'd very often encounter if you're doing algorithm analysis. So these by no means is this a complete list. You can think of this kind of like a baby step towards the kind of things that you can find that you can quickly use. And in many instances, you're going to run into this. So one of these will probably be something you'll run into. Not every one of them, but most certainly a good chunk of these. Some of them you'll run into so often you'll just memorize it. And that's often the point I try to get to when I talk about a lot of this sort of stuff. So let's talk about, so usually in an algorithms class, very often people won't expect you to memorize all of these, usually just a subset of them. However, I can't tell you what every prof wants you to do. So the point is that a lot of these are very common in algorithm analysis. Likewise, you might ask, Dan, what is a closed form? So imagine I give you my general or explicit formula for a given term. Now, what if I wanted to have something like that, but for the entire series? That's what a closed form expression is, or closed form formula is. So you know how we have like a general or explicit formula for a given term in a sequence? You can imagine the same concept, except now we're going to talk about the whole sum. So now I want to know what's a formula for calculating the entire sum. That's what a closed form or sum or product, whatever would be for the operator. That's what closed form is. The nice thing with closed form expressions is they typically are very easy to compute. Often, at least the ones that you'll run into. No, I can't claim that all of them are. Most certainly there's some really strange ones out there. But the ones that I'm going to show you here are rather nice. That's the point I'm getting at. And usually they involve computing a constant number of operations to do it. So that's another perk that they also have very often. So here are some common ones. So the first one I already told you about earlier is the arithmetic series. So the sum from I is equal to 1 to n. You keep in mind it could be a 0 here. It doesn't make any difference. Where the summed or general term is I. Now you might ask, Dan, what the heck is that? So I'm going to give you one way of thinking about how you can derive what a closed form would look like for this. So remember, the goal I'm coming up for here is I would like a general formula for any arbitrary n for this given guy here. So it has to be like n is 1, n is 2, n is 3. It has to work for all of those values. So I have 1 plus 2 plus 3 plus 4 plus 5 all the way up to n. I would like to have a nice formula that takes a constant number of operations for me to perform that tells me what the sum actually is without having to calculate each one of these terms separately. So, because remember, if I were to do this mechanically, say algorithmically, I would have to, if I literally were to calculate this out, I would have to sum up each one of these, which will take n many additions. Sorry, not n. Because it'd be technically, either way it'll be big O of n. It'll be big O of n many operations that will have to happen. So I want to show you how you can do it in constant time. Okay, so that's what I'm saying. So anyways, you might ask, okay, so Dan, what exactly do you mean by this? So what I would like to have is a formula that if I pump an n into it, it should tell me what this is. But I want it to be something in terms of n. So here we go. Here I'm going to give you an idea of how this will work. So this is a nice, cute way of coming about this. So if I had f of 1, suppose that f is going to be my function that's going to represent the sum of all of these terms for up to n. So it starts at 1, goes up to n. So if it's f of 1, that's just 1, right? So I'm going to represent that as a box. So I'm going to represent that as a box. And then next, imagine I want to consider f of 2. That means it's 1 plus 2. Well, how many boxes are there? 1, 2, 3. There's 3 boxes, right? Okay, how about f of 3? Well, think about it. You start off with 1 plus 2. So far I got 3 plus 3 gives me what? What does it give me? Gives me 6. So far I got, so when n is 3, it's 6, which matches my boxes, right? Well, I can keep doing this, right? So I can keep going until I consider n. So eventually I will consider when I have n. So I want you to look at the heights of these boxes, okay? So this one has height 1, that has height 2, this has height 3, this one has height n, right? And I might say, Dan, where are you going with this? And I'm going to show you how this works. So watch this. So we know that if I were to count up all these boxes, that would tell me what this sum is. So let me show you a neat geometric trick for how you could derive this closed form expression. So what I'm going to do, because you would agree with me, that if I were to know how many boxes there are, which is equivalent to me asking what the area is of all of these boxes, if they're all 1 by 1 squares, right? That'd be the same thing, right? What I'm going to do is I'm going to take my jagged looking triangle and I'm going to mirror it on itself across the diagonal like this. So what I'm going to do is I'm going to have it where I have one box right here for that one. So I'm going to imagine I'm going to take it like this. So I'm going to take what I have here, I'm going to fit it around so it makes a complete square or rectangle. So it'll be a rectangle. So I'll have one box, then I'll have 2 boxes, then I'll have 3 boxes, and so on all the way until I have my n boxes, right? When I introduce this stack of new boxes, like this, what's the height of all of these? They're not 1 anymore. This is now, I add n there, I add n minus 1 here, I add n minus 2 here, here I add 1. So if I look at this as one big rectangle, what's the dimension of this part of the rectangle? Well, I say it right here, it's n plus 1. All of these are n plus 1 now. So it's n plus 1 now on that side of the rectangle. How about this one? Well, we know it's n. So it's an n by n plus 1 rectangle in its dimensions. But here's the catch. Here's the catch. What's the area of the black squares? Well, let's think about it. The way I built these red squares was just simply taking the exact same number of boxes and mirroring it like this. So the area of this whole rectangle is twice as big as the area of the black squares. So if I want to ask what the area of, or how many boxes there are, well, it's the area of my rectangle, which is n times n plus 1. And since the black squares comprise half of it, there you go. And that's your closed form expression. So no matter what n you put into this that fits this form, you will get this guy. And that's an example of a closed form formula. So I will later, after I go through this list, I'm going to show you how you can prove this using a different technique. So I'll be showing you how to do it with mathematical induction. This is more of a cute geometric argument. There's many proofs for this guy over here. Just a cute picture, okay? So with that being said, let's keep going here. So this is one right here. Here's another one. So suppose I have the square numbers. We talked about those earlier. Suppose I want to go through each one of my terms here, and I'm going to sum them up. So I have 1 squared plus 2 squared plus 3 squared plus 4 squared. And I must stress that this is I squared. It's the term or summand for this summation, okay? This is n times n plus 1 times 2n plus 1 divided by 6. And you might ask, Dan, where does that come from? Well, let's think about it. So I'm not going to go too deep about this one because I want to respect your time, because keep in mind that we're going to be doing a bunch of other stuff here today. So I'll give you kind of a flavor of it. Do you see that there's an n times n plus 1 like we had there? That's not a coincidence, okay? So one thing I'll give you as a tip, especially for algorithm analysis classes, know this one. That one's your best friend. It's always your best friend. I will tell you, I've given numbers of exams where I just expect you to know that one, say for courses. Here's another one that is another one of your best friends. This one I will convince you of, or at least I'll hopefully convince you on. This is another important one. So I'm going to assume that I am given A and B, which are going to be integers. So for those that aren't acquainted with this notation, this means in, and this is the set of all integers. So this includes your counting numbers, also includes the negative numbers, and it also includes 0. And I suppose I give you a real number, C. So this blackboard R means the set of all real numbers. The blackboard Z means the set of all integers. And it's that A is less than or equal to B. Then the sum from I is equal to A to B of C. So it means that all I'm doing is adding a whole bunch of C's together. And I must stress, if you don't like C right there, you can just put 1 right there, just to help you see what's going on here. This right here, you might ask, okay, what's that? Well, For the sake of discussion here, I'm just going to presume that A and B are integers, but not just that, they're going to also be positive, okay? But I must stress that this works regardless. Just the point is that A has to be less than or equal to B. So I'm just going to keep this simple. So remember, let's understand what this means. So it starts off at A. So we have, for A, so when we have value A, we have a C. For value A plus 1, we have a C. Plus another term for A plus 2. All the way up to eventually you're going to get B. So for the term for B. So the question is, okay, so how many C's am I adding? Well, let's think about it. For the sake of our discussion, remember I'm presuming that there are a discrete number of these. That exactly is what's happening, right? So how many C's am I counting up? Well, let's think about it. If I had B many, that would be starting off at 1, right? I would have go 1, 2, 3, 4, 5, 6, all the way up to B, right? If I go from, so if I have that, then I take away those that go up to but include A. How many of those are there? Well, I'd be cleaving off some number of these if I included a whole bunch before this, right? But these ones are definitely in the sum. So again, in a very similar fashion, you can imagine I'm adding a whole bunch more C's. But these are all the ones before that. So this would be for like term 1, term 2, all the way up to, I guess it would be another one in here. Sorry, there's supposed to be dots right here. It sort of melted into the plus signs, okay? So this right here, this will be term A minus 1. So the true value for this sum will be when I get rid of all of these. Because truly, if I start this off at, say, 1 or 0, you know how many B's there are, right? Right? So you know that, okay, if it starts at 1 and goes up to B, that means that you have a C for 1, a C for 1, sorry, C for 2, a C for 3, C for 4, C for 5, C for all the way up to B. That means that there's B many of them, right? There's B many of them if you start at 1. So you know that there's going to be B many if you started at, say 1, right? Then if you wanted to start at A, what's the first thing I can think of trying to do? Get rid of all the ones that go up to and include A, right? So there's going to be less A many terms. But you'll notice right away, if I just do this, I'm actually cleaving away this one right here. So I actually need to add in one more term. Because I would be getting rid of too much stuff. So I add one back in, because remember, the index when I is A is in fact an element that I am counting over. So it's C times this. And this is the number of C's that I'm adding up. And I must stress that A and B can be any integers as long as A is less than or equal to B. What's actually happening as a mechanism with this sum is that I'm asking how many times am I adding up the summand. That's all that's happening. So this one's another one of your best friends. If you know these two, I think you're doing pretty good. So if you get yourself playing around with the analysis of algorithms, you'll find that these two are your most common friends you're going to run into. This one not so much, but these two most certainly. So here's some more. I'm going to dish out some more. These ones I'm not going to say as many things about. So I'm going to have the sum from I is equal to 1 to n of I times I plus 1. This is going to be n times n plus 1 times n plus 2 divided by 3. You might ask, Dan, what is that all about? I won't have enough time to talk about it, so we're going to proceed to the next one. I do always have time, but most certainly I'm just joking around. I just want to get to some meaty, juicy stuff, okay? So right now we're just kind of going through a list, and I'm trying to justify some of the ones you're going to really want to find useful to use all the time. So the next one I want to give you is, okay, I already did D. I'm getting ahead of myself. E. So my next one I'm going to show you here is, this is, for those of the purists in the room, you'll very often call this the arithmetic series. So the sum from I is equal to 0 to n minus 1 of a plus I times d. So I is the lower limit here. Sorry, the variable I'm using to iterate over this is to be n times a plus d times the sum from I is equal to 1. So I is equal to 0, sorry. Doesn't make much of a difference, to n minus 1. Well, if you know your closed forms from over there, if you just simplify this, you'll end up with n times a plus d n times n minus 1 over 2. Now you might ask, Dan, where the heck did this n times n minus 1 come from? Well, remember, in the first one I gave you, the upper limit is what appears on the right-hand side. It's the upper limit times the upper limit plus 1 divided by 2, right? So, well, what's the upper limit here? It's n minus 1. So it's n minus 1 times the n minus 1 plus 1. That's what this comes from, and there's your divided by 2. This one you could derive from that one, which is why I never really think this one's too terribly important to figure out on your own. It's just a simple little exercise from that one. So next, we're going to get a couple juicy ones. This one I will prove for you at some point here. So for some real number, which is going to be r, which is very commonly called the common ratio in this context. It's not going to be equal to 1 in our case, but I must stress that there's ways to generalize it so you could have an r that's equal to 1, but it honestly collapses into C over there. It just collapses into that one, if my memory serves me correctly. Any integer n greater or equal to 0. You might know this as the finite geometric series. So the sum from I is equal to 0 to n of r to the I is equal to r to the n plus 1 minus 1 all over r minus 1. So you know this one is the finite geometric series. You run into this guy whenever you're dealing with, well, at least one example I can give you, because I can give you tons of examples where this comes up. One place where you could run into this guy is when you're dealing with things that are growing exponentially large, hence the geometric growth that characterizes the geometric sequence. So very often you run into this guy when you consider the opposite. So for example, when you are trying to analyze how many times you have to apply a given function call, and say this is happening exponentially many times, or even the reverse of that. Say a logarithmic number of times. Usually the logarithmic number, sometimes it grows, like you're trying to figure out the powers of 2, and you ask, how many times did I have to go for the powers of 2? Sometimes it pops up with this guy. Somewhere pops up. And then you just take the logs of both sides. It happens. I'm just saying. Here's a variant of it that I like to give students because I just like it. It also is easier because you're dealing with, like say if you have a lower limit and upper limit, you want something that's easy to play around with. This is your variant that's your friend. You can derive it from this one, by the way. For some real number, r is not equal to 1, and you have non-negative integers. Non-negative integers. This integer, by the way, is just sort of melting there. The n is just looking like it's turning into an h. It's just happy, okay? Integers, L and U, where L is going to be, L is less than or equal to U. Here's how I'm going to write this out. So you're going to see that this is actually just a specialization of this one right here. I is equal to L. So it goes from I is equal to L to U. A times R to the I, where A is just some real number. This is going to be equal to a times r to the L minus r to the u plus 1, all divided by 1 minus r. And again, if you find yourself wanting to look at this and be like, Dan, I'm not convinced that this is true. What you do is you take this guy right here. And the reason why you'll notice that I make L and U non-negative integers is the technique you use is actually one of the techniques I'm going to show you here shortly. So you just apply, like if you wrote out this, you could rewrite this as a partial sum of one of the parts and one for the other part. Apply this for each one and then simplify and you'll get this right here. Let's kind of go through the fun exercise of applying closed forms. So I'm going to give you some, you can call this like Dan's fun bucket of tricks for simplifying summations, but I don't claim to have been the one to come up with these. These are just some very basic ways of manipulating summations. I'm just being a little playful here. So let's talk about simplifying summations. So, here are some common tricks. So the first one I'm going to give you, it's going to be this. So what I'm going to do is I'm going to do them in the form of examples to illustrate the technique. But I'll have more thorough explanation, like just some sentences in that in the notes here. So anyways, suppose that I give you a sum from I is equal to 1 to k of I minus 1. Now there's several different ways I can go about trying to make this look like the closed form I gave you earlier. So you can look at this and say, oh, well, it looks kind of like I, right? So what if I can make it look like that? So this is where I'm going to pull out those properties I showed you earlier of properties of summations. So what the one way I can do this is when you have multiple terms inside of a summation like this. Notice we have I and we have minus 1, right? What you could do is use the distributive property I showed you earlier, right? So I could split this into two summations. Take note that these limits don't change. You can't change them. You have to be a bit more careful when you're doing that, if you're going to do that. I'll have more discussion about that when we get there. So notice I've distributed the terms akin to what we talked about earlier. Now, this looks like something I can apply the closed form formula to, and this also looks like something I can apply a closed form formula to, right? So that's all I'm going to do now. So this, the upper limit is k, so I write k plus 1 divided by 2. Please take note of the lower limit. The lower limit in that case, if I use this, has to be either 0 or 1. The reason why it's okay to be 0 is because it's 0 plus everything else, right? So I have that. Subtract off whatever this is. So what's that? Well, it's 1 times the upper limit minus the lower limit plus 1. But it's just 1 times that, so I'm just going to write this. Okay, I'll put the 1 here, just because I want to be helpful. So now, what's that over there? Well, the 1 times all of this, just for the sake of space. Minus 1 plus 1, those annihilate each other, and I end up with just k, right? That's just k. So let's put this all together now. So what I'm going to do is I'm going to make a common denominator. So I'm going to multiply this by 2, make it divided by 2. So let's put it all together. So I'm going to expand this out just for the sake of ease. So I'm going to make this k squared plus k minus everything that would be associated with this. So that's k, but I'm going to make it over 2. So I'm going to make it twice as big, right? Because it's over a common denominator. So note that this is no different than me writing 2k divided by 2, right? And then I'm going to simplify. So notice I have k minus 2k, so that's minus k. So I have k squared minus k over 2, which is just this. If I factor this, notice I have k's here, so I'm just going to take k times k minus 1. Because notice you can convince yourself of this just by going, okay, k times k is k squared, k times minus 1 is minus k, right? boom, boom, right? So the first thing I can recommend is if ever you're dealing with something you're not sure about what to do and it has addition or subtraction in here, just distribute it. Don't put yourself through that. Distribute the work, okay? Next, sometimes it's helpful to take and write out what the sum actually means. So akin to what we talked about when we talk about sequences, where we're trying to find a pattern, you could do something very similar to this, except you're trying to group terms because you're adding them, right? So if you can group the common terms, you can rewrite those as sums, and it may make it easier to work with. So let me give you one that actually has some numbers in it. So the sum from I is equal to 1 to 400. Yeah, I'm going there, okay? And we're going to make it an alternating sequence inside of here. So I have -1 to the I plus 1. For those that aren't initiated from earlier, when I put 1 in here, notice it's 1 plus 1, so that'll make it 2. So it's -1 squared, which makes it not -1 anymore, it's +1. It flips the sign, okay? That's what we call it. Say it's alternating. So notice it will alternate back and forth, back and forth, back and forth. So that intuition is rather helpful, but I'm going to make this even more interesting. So I'm going to multiply this by the ceiling of I over 2. Now, for those who have never seen the ceiling function before, that is simply, I take whatever the result of I over 2 is, and I'm going to round it up. And I mean straight up, just like, if you give me 2.3, and I apply the ceiling function to it, I want 3. You're going to, so when you have a choice of rounding down or up, you're always going to round up. So if you have a fractional part that makes it so it's slightly bigger than the current integer, it goes up to the next one. So just like if I had 2.5, the ceiling of 2.5 is 3, and it doesn't matter, it could be 2.001. That's 3. My little turtle friend fell down. We gotta help him. Let me go get him. There we go. There we go. So does everybody understand what the ceiling function's all about? So all it's going to do is divide by 2, and I'm going to, whatever the result is, it may be a fractional number, I'm going to make it so it's the next highest integer if it isn't an integer, okay? So let's see what this means. So let's try putting in 1. So 1 to the, let's see, 1 to the, so that, remember we said that's just 1 times 1 over 2. Rounded up is just 1 over 2 is 1, right? So the first term is 1. Next, 2. So that's 3 up there. So odd exponent means it's going to stay negative. 2 over 2 is just 1, right? 3. Okay. 3 plus 1. Okay, now it's even again, so now it's positive. And then 3 over 2 is just 2 when you round it up. Do you see anything interesting going on yet? So it's 1 minus 1, 2. Let's go to the next one, 4. So we have an odd exponent, makes it negative. 4 over 2 is 2. Now it's minus 2. So we got plus 3, minus 3. And so on until you get plus 200. Minus 200. That 2 is looking a little bit cramped there. So now, notice very quickly that I have, so some people would call this a telescopic sum. So what it means is that I've expanded the sum out so that now you can see that there's actually parts that are going to cancel out each other like this. So I'm going to rewrite this for the sake of our exercise as 2 new summations that are simpler forms that you know how to play around with, okay? So keep in mind that if you can immediately see that these are going to annihilate each other, which is what they're going to do, I just really want you to see that really I can get creative and reformulate this. So I can take all the positive parts, I can add up all of those in a sum, goes from 1 to 200, and I'm going to subtract off the sum from I is equal to 1 to 200 of I. So those are all my negative terms, right? I'm going to apply the closed forms for each one. 200 times 200 plus 1 divided by 2 minus 200 times 200 plus 1 divided by 2. And this is just equal to 0, right? These are the exact same quantities due to symmetry. So you could have stopped right here the minute you've seen it, but I just want to show you that you can take a more complicated sum like this, reformulate it as much simpler sums that you know closed forms for, and then you could play with it from there. So this is just meant to illustrate that you could reformulate that more complicated looking sum as something much more friendly that you could play around with, just like a cute little kitty. So the second tip, if you're ever unsure what the summation means, just write out what it means. Remember, it's just a sequence of terms being added. That's it. So now, I'm going to give you one of my most important tips. This one I think that a lot of professors don't spend enough time showing. And I'm telling you, in research I've done, like when I was doing some of my first research, this tip, not necessarily in the context of summations, but generally in the context of combinatorics, saved my butt. I'm telling you. It's a very helpful thing to keep in mind. Because sometimes you have a closed form that doesn't have quite the form you have for currently what you got. So what you do is you try to make it, massage it a little bit. So you're going to remove or add terms to quote unquote massage the summation into a closed form. I'm telling you, this, if there's any of these tips that I can take with you, other than number one, which is you're going to use this one a lot if you play around with summations, this one, it will save you time sometimes. That's me covering my butt. So, this is a very elementary example of for number 3. I'm not kidding, it'll be your best friend. So I have a sum from I is equal to 3 to k of I. Now, notice it does not fit the form of the closed form. This has to be a 0 or a 1. Now, the next technique I'm going to show you after this is far more prominent. At least if you take some of these kind of classes. It's called, so what you do is you substitute the lower and upper limits of the sum, and then you adjust what's the sum inside there to accommodate for the shift that you make to reassign the values for the lower and upper limit, which I'll show you how that works in a moment. But I want to show you what you could do with this that honestly, in many situations, it'll be good enough for what you're up to, unless you're specifically looking for a specific way of applying this. So notice I want this to be a 1 here. Well, what is this? It's 3 plus 4 plus 5 plus this plus 7 plus 8. Sorry, I'm just running out of my words here. 7 and so on, all the way up to adding up to k, right? That's what it means. Well, what if I were to stuff in 1 plus 2 in it? So it makes it look like the form. So I go 1 to k of I. We know what to do with this, right? We know what this is. This is k times k plus 1 divided by 2, right? But remember, this is me fudging it. We don't want to fudge it. We need to make sure we add back in or take away what we just included. So we added in a couple of terms in here, so I'm going to remove them now. Now, if you have many, many terms, you might write this as a summation. For the sake of simplicity in our example, I'm just going to write them out explicitly like this. So that's 1 plus 2 there. Notice that if I subtract this off of this, I'll get back that one over there. So I already know what to do with this. It's k times k plus 1 divided by 2 minus 3. Boom. That's it. So I wanted to show you a very basic example because I know that if you see this, you'll be like, dang, that's nice. So anyways, let me show you another one. So this is the last one, and this is the one I warn you is the trickiest of these to apply. If you can get away with doing this, go for it. But some people prefer this approach. It sometimes actually can be handy when you're dealing with multiple sums. So what you're going to do is you modify. Another tip is you can modify or modify the lower and upper limits. So when you do this, you have to update the sum end appropriately. And I'm going to show you an example of what I mean by this. But I must put like exclamation marks, okay? To be careful when you're doing this, because I find students very commonly make mistakes when they're first trying out using this approach. So let me show you an example. So I'm going to assume k is going to be greater or equal to 2, and we're going to let this following function be as follows. We're going to let g of k be the sum from I is equal to 3 to k plus 1 of 2 times I plus 2. Two things. The first thing is that you know actually how to play around with this if you use the previous technique. What you could do is you could just simply remove. So what you do is you add in I when I is equal to 1 and I is equal to 2. You end up with that being 1 to k plus 1. You could play around with that, apply technique number 1 and distribute it, and then play with it from there, but make sure you obviously take away the extra terms. So that's one way you can do this. I'm going to show you another way, okay? So to make this look like something that looks like one of my closed forms, I need this to be a 1, right? So I want the lower limit to be a 1. So what I'm going to do is I'm going to create a new variable. So I'm going to create a variable j, and it's going to represent whatever I is, but I'm going to knock it down 2 increments so that so it would be like if I crossed out this and I put j is equal to 1. So to make that happen, I take whatever I is, and I'm going to remove 2 from it. So it looks like 1. Okay? So that's what I'm going to do. I'm going to introduce a new variable. That's going to be what I'm going to use for my counting here. So I need to update them carefully, though. So now the lower limit, the new lower limit, is as follows. It is now j is equal to 3 minus 2, which is just 1, as I said. And now we got to take the upper limit. Since I've shifted the lower limit down by 2, the upper limit has to go down by 2. The new upper limit. That means that if I look at this, it's k plus 1, but I need to knock it down by 2. Because I need to do this so that I ensure there's a proper number of terms. I don't include extra terms. Now, that isn't all I have to do now. Notice that this guy had an I in there. So everywhere where I see I need to put in whatever it would be in terms of j. So notice I have this lovely formula I cooked up. So wherever I see I'm going to replace that with whatever it would be if I wrote an I is equal to whatever else is there. So I'm going to rearrange that equation. Notice that this is no different than me writing I is equal to j plus 2. So notice I could just add 2 to both sides of this equation. I end up with I is equal to j plus 2. So that means that the sum end needs to be updated, right? So the new sum end, wherever I have I, is going to be replaced with this. So I'm going to put j plus 2 wherever I had I. So 2i plus 2 becomes 2 times j plus 2 plus 2. So now the new sum, so the new sum looks like this. So the new sum looks like this. So it's the sum from j is equal to 1 to k minus 1 to k minus 1 of, okay, well, let's just simplify this as 2j So we've got 2j. So we've got 2j plus 4 plus another 2, that's 6, right? So this would be 2j plus 6. And now after this stage, and this is what I'm going to encourage you to try doing, is finishing up this example. Just apply technique number 1, okay? Now that you have it in a form that you can easily apply the same technique. In this case, what you would do is you'd split this into 2 parts. So you'd have 2 parts like this. So you have 2j, and then you have a 6 like this. And then notice that you could take this 2, you can factor it out in front like that. But I'll let you think about it, okay? So those are some common techniques for simplifying summations so that you can get a nice closed form expression.